sign to put to an orbit. Now it's an interesting picture of how dynamic things are and how hard it gets when it comes to actual prediction. So we saw the Parker spiral, right? And you have all those blue lines are basically Parker spiral, except that here you have a CME that's propagating across the interplanetary space. So you have everything being, distorted, because of that motion of this CME, and then you have a solar flare simultaneously going up, and that's doing something weird. So you have all sorts of things going on here. So you have the stereo B, which is receding Earth in its motion around the sun, and then you have stereo A, which is ahead of the Earth. So you have two different satellites. But if I were to look at stereo A, and you have a high streaming, a high energy particle coming to me and say, yeah, there's something going on here, and then nothing happens there because this is way beyond, it's way behind in terms of time. So what happens is, things happen in a different time scales based on what you're looking at. So not everything is going to happen in a flash. The high energy particles are going to come streaming first, and then you have some big cloud of dense gas that's coming later, and then you have magnetic field coming at some point in time. So all this in some different levels is going to make things harder for people to predict. So that's why trying to understand the geometry and direction it's a harder science than anything else here. So everything is happening at a different rate, everything is happening at a different time, and everything has a different scales. It makes it extremely hard for us to predict. Now, the way they do, of course, we have to find a way to actually at least get into a frame of mind where we have control over a few things. So L5 and L4 are what we call as the Lagrangian points. I mean, to explain that, Lagrangian points are an interesting point in space. I mean, it's not like a fine point, but it's this region of space. Now, every object has a gravitational effect. I mean, two different objects, one is going to exact gravitational force, and the other is same thing happens on the opposite side. So there are locations between sun. I mean, this is sun, this is Earth. There are points between Earth and sun, which is L1 point and L2 point, where the gravity of the sun is going to balance off the gravity from the Earth, which means you are left alone in this orbit. So as somebody sitting in L1 orbit, you're going to go around the sun at the same rate as the Earth would go around it, which means you have somebody watching you up close before something hits us. So that's the neat thing with having something at the Lagrangian 1 point. You also have a Lagrangian 2 point, where if you measure the gravitational force to this point from the sun, that's going to have a positive force, and then you have a negative effect coming because of the Earth. It's going to cancel out the same thing. Here, same thing, because these are gravitational potential wells which help us design satellites. So once we put them in orbit around that point, they will stay there forever. So that's a cool thing. You don't have to manage them. So as long as you have some amount of fuel left, you can manage them to be in stable orbit. But that's the nice thing. It doesn't go around the sun, it doesn't go around the Earth, just like other geostationary satellites or field satellites. They have a far more stable orbit because of that help that we get from the sun at the same time. So that's the cool thing with that. Now, this is just one slide where I have some kind of math thing, but it's not too complex here. So you have the Earth sitting there, and we have a sun sitting there. So on our scale here, so we have X and Z and Y. X is always pointing to the sun, Y is the opposite axis, and Z is the rotational axis. The interesting thing here is the actual dipole axis. We saw a bar magnet right in the beginning of the talk. That bar magnet is usually like 12 degrees, approximately 11 degrees off of the actual rotation axis of the Earth. Okay, because of which you will have some things happen because of the seasonal effects that you've heard because of that. But the whole point is, if Or if the sun were to stream something at you, okay, if you're getting some magnetic field, this is what things might look like. So you have magnetic field looking at this. So you have the Z there, you have the Y there. You measure, all you have to do as an instrument is just have to measure this angle, which will give you an approximate way to compute the energy that's coming from this. As soon as I know what's the speed, what's the magnetic field, what's the angle, I know how much energy is going to be dumped on. Okay. So the key to finding these things lies in how precise you can be in terms of calculating the angle of theta or clock angle. The more you miss, the worse it's going to be for in terms of prediction. So another challenge is in space where there's also measuring the clock angle of the magnetic field. That's also something, it's a key element of space weather research. So going back to the same picture here, so you have an instrument that's measuring the solar wind particles. It will measure the speed, it's measuring the magnetic field, and then it will transmit the speed within few seconds, within few milliseconds that you can process, right, before something hits us. Now the cool thing is, this L1 point, or the satellite which is sitting at L1 point, is far ahead of this bow shock which we saw earlier, because bow shock is where the contact point is between the solar wind and the Earth's magnetic field. If you have anything before that, you are better off, because everything before that is what's more exciting as a space forecasting, because you have a lot of headway, you have a lot of time available for prediction. So as soon as that information reaches us, we know there's storm underway based on the data that we're getting before it hits the Earth. And then we can start your model to compute those things, which will give you a precursor to what's going to happen. That's the cool thing with this L1 position. Now, people always call this the Sentinel forecast. And obviously, if you've been to this, Buckingham Palace in London, you'll see the guards waiting. That's like the first line of defense. And it doesn't mean anything these days, but that's like the first line of defense. So that's the first line of defense we got from a CME or anything. So if there's any change in the fluctuation velocity of the magnetic field, L1 point is going to give us this alarm, and then we can do something with our satellites and we can go and hide. Just to give you a brief idea, so 1A is approximately 149 million kilometers, so the speed of light is going to take approximately 8.5 minutes to reach Earth. The solar wind, we know, we saw it was about 400 kilometers per second. So L1 point from Earth is about 0.998. If you do the math, you get this time is about 15 minutes of notice. 15 minutes of notice is sometimes really, really big. It may be less, but it's really high. If you're looking for a hurricane, 15 minutes is nothing, but in space weather, 15 minutes is a lot. So you look at this. So we saw the magnetic fluctuations, and as I say, I'm coming at you in this direction. One time I may come at you in this direction. So this is the hardest thing. You don't know the clock angle. The clock angle is constantly changing. If you know the clock angle, it's $1 million question you can solve. Sometimes it's harder, but there are times when sun is showing mercy on us, especially like a classical case like this. You look at how the clock angle changes across this plot. Now, at the same time, watch what happened to this. It took a dip. Every time you have this kind of a pattern, especially when you have extremely negative BZ, you will have a high impact activity on Earth. That's always the case. More often, this is not something that is going to, in real sense, this is not always that happens, but it might happen once in a while if you're lucky. This is the actual data. This is not a model data. This is the actual data, and this is the actual result. So this is not how things are in reality. In reality, this is how it is. It's going to be extremely complex. It's going to change all different directions. You're mainly looking at something like a protein structure. It's not that easy at all. Another cool animation here. So you have the Earth with its magnetic field, it's the magnetosphere, and then you have solar wind coming, and then that deflects off this field, so the field direction changes, it's pushing inwards, and then you have so much energy that's being dumped in here that it becomes so unstable at that point. It brings in all the streaming electrons into the Earth through the poles to create this nice auroras. So this is what happens. This is exactly how auroras happen. So when you see aurora, it's always an indication that sun has been extremely active. So next thing is what I'm going to switch gear and talk a little more about why on earth we are not quite safe as we think we are, because we're safe here. I mean, what's not safe is like just the infrastructure we have in space. I mean, we can't do the GPS. We can't. We have International Space Station. We have so much satellites. Everything is in a constant orbit. When things stream at us, these are the things which are at high state. You have part of the bridge being affected because of the solar storms and a lot of current and energy that's coming from it. That's why you care a lot about these things. So when you have solar energetic particles, just look at the approximate time frame here. Anything about excess of 5 MeV, I mean, let's forget about what MeV is. Just it only takes 8 minutes for photons and any electric particles to reach Earth. Just 8 minutes. You can't do anything in 8 minutes. About like 2.5 hours if it's just a 1 MeV electron, but at least you have something available for you if it's a slow-moving particle. If it's a fast-moving particle, you rarely have any time. So, but often in times, this is what happens. I mean, this is the measurements this was again the same storm that I showed you earlier on. This is something early in 2012. And you have a sudden peak in the measurements of this high energy particles, extremely sudden jump within like a few minutes or so, and you barely have any notice. And this is what happens. It knocks off satellites that are supposed to do data for space weather. I mean, this is the real situation we face. So, given the time scales here, if it's an X-ray, it's fast. X-ray travels the speed of light. Basically, I have no time at all. Look at the time here, 1 minute. Then you have radio bursts. Radio burst happens when you have a shock wave that's propagating because of this CME. When you have a coronal mass ejection, you have a slow-moving a beam of solar wind, and then you have a fast-moving shock, and these creates what you call this solar radio burst right in the beginning of the CMEs. And the CMEs originate from the sun first in happens. You will see lots of radio bursts going up, and I mean that's by far the hardest thing to predict. Scientists today, the radio burst, and absolutely you have no notice at all for the radio burst. Energetic particles, as you said, depending on how energetic they are, they could be as low as 20, 30 minutes to about a few hours. So you have some way to deal with those. But again, the warning goes off right when the flare goes off. So as soon as the flare goes off, they put up the warning there. And solar plasma, because they're only propagating at 400 kilometers per second, and that's roughly about 50 hours. 50 hours is a pretty good time. Which is where then you start just watching, and then you put a warning like a few hours, and most computer models these days can do a good job on this part of the plot here, especially because you have plenty of time to do the calculations. So I think we'll skip this part. What about solar minimum? Is solar minimum any good? Not quite. I mean, you may not see that many storms during the solar minimum, but it's still quite complex. Even the solar model, you have things like a fast-moving a streamer that's bumping into a slow moving shock creates shocks, and you have a compression zone like that, and you have rarefaction. So all these complexities, even during solar minima exist, so you're not completely out of trouble there. So things may be lower, but it's not completely out of sight. So models of the sun is probably not easy to understand, but it's a lot more difficult if you're looking at a solar max solar magnetic field model example look right like this. So that's the whole idea. Solar minimum is fine, but you still see a lot of storms coming bigger, even during solar minimum. So we have so many models that have slowly been evolving over time. I mean, these are like end-to-end models. End-to-end meaning like from the sun to Earth, and now doing nice space with the predictions. So if you have an L5 monitor like the stereo satellites we saw earlier, sitting at here, and you have the stereo satellite sitting at B, and then you're monitoring the Earth. I mean, since the way the Parker spiral looks, sometimes Mars can get the first effects before we feel here at the Earth. So that's how it is. You might think Mars is behind us. No, not because of Parker spiral, because the geometry is so different when you look at the Parker spiral. Mars can get the first impact, and then we can later. So these things are harder than we think it is. So models are really slowly evolving. So I mean, it's just a nice cartoon of the CME going off, and then how things evolve, and then it hits Earth. So this is just going into the time space. Any green is low levels of activity. Any blue or any red is extremely high level of activity. So models are there to give us a nice feel for what the eventual effect is going to be. So anyway, so switching gears here, like the final part of the talk, I'm going to talk about some technological impacts. So radiation, as I said, if you're taking space flights, obviously, if you're looking to go into ISS or somewhere like that, even for people who are taking a polar route flight, if you're flying from, let's say, Canada to Hong Kong, the easiest way to is just fly around the poles instead of navigating around the Earth. So sometimes United or any major island that's flying at, flying those kind of flights, they want to save fuel too. Obviously, it's much easier, cheaper to run, to fly to the poles. And the problem is during intense solar activity, it's not quite safe because of radiation. And also because your heads of communication, which is what primarily the pilots use to communicate with the ground station, is going to be affected. So because of these reasons, it's not quite safe. So even they have like space to the forecasters to kind of give them an idea. To give them like a 3-hour notice, United is not going to stop their flight. If you give them a half day or maybe 1 day notice, maybe they can reroute their flight to a different direction. So that's extremely important. So astronauts, same thing, radiation, because most of these high energy particles are extremely ionizing, and they happen so fast that you don't have time. So they probably have to not take like a spacewalk or something. So that's something you have to take care of. Spacecraft stem cells, like surface charging, these are basically electrons, moving currents, moving particles, create currents, create currents, interfere with your parts, and that creates problems. And then you have extremely high energy particles creating a single beam absence. Edge of communication, GPS signals. GPS signals are extremely bizarre because lower down in the atmosphere, you have a lot of atmospheric scintillation. I mean, this scintillation is totally different from what astronomers talk about. That scintillation is different. So this scintillation creates ionizing effects that will change the way it computes. So you have propagation problem between you, the device, and the satellite that's giving you the signals. So what happens is, end of the day, you're going to have wrong calculations being put out by GPS signal. It's not something that's used for street navigation. Street navigation, you don't have to be extremely precise. But for people who really depend on GPS for high precision research or high precision work, like I guess people always use this in the oil industry and stuff. I mean, they need high precision GPS signals. But there, this is extremely critical. So we have a way to even like tackle that. Like there are like loss-enabled GPS, which is called the wide area augmented system. These have a way to incorporate the changes that happens in real time and then bring that information to your through your GPS, that will give you the correct data. So that helps a lot. Power grids, back in 1989, if you're from Canada, you know that Quebec City lost, had a blackout like in a flash of a second, and that's because of overloading because of solar flare. Because what happened was all these ground penetrating currents were overloading the generators, overloading the power grids, so you have to go for a blackout. So that's something that's extremely catastrophic if something like that happens here. Oil pipelines, again, oil pipelines always carry a lot of oils, and obviously they have acids too, so they have acids that's building up because of the charged particles, and that interfering with oil pipelines can have problems in terms of leakage and stuff, so they are very extremely careful. And finally, the satellite orbits, because of scintillation effects, satellite orbits can change by itself, because the density changes, it will have some drag, which you unwanted drag, that will take the satellite in a different orbit. So you have all sorts of problems everywhere. So it depends on who you are. Because all this happens in a different time scales, right? I mean, for a satellite orbit, it's slower because that's not going to be affected by the high-speed electrons. But your GPS signals probably wait for a couple of days. Your HF communication or for your, for your radiation, there's absolutely no warning at all. So it depends on where you are and what the consumer is, and you react accordingly. That's what you do. It's a nice picture basically telling what I just told you. So you have solar radio bursts coming from the CMVs, and that can cause GPS signal loss and things like that. And astronauts suffer because of radiation and ground penetrating currents can actually cause power grids to fail. And we have earth currents, which is interfering with the oil pipeline. So depends on who you are and depending on what time scales you're looking at. So some of them are extremely critical, some of them may not be, but it's always, everything is going back to sun. So this is something we do advise. So if you'd like to subscribe, I mean, it's also one way for me to promote our work. You can subscribe to that. I mean, we do send out alerts every now and then when there's space for further activity. Not only that, I'll also tell you if you live in northern part of the US or in Canada, whether or not you want to see a alert. So that might be something exciting. So if you want to sign up for that, feel free. That's free. So we're a great audience, and if there are any questions, thanks a lot.
Do Mercury and Venus get hit harder than we do because they're closer?
It may be, yeah, definitely. They're much closer, and in fact, well, again, it's always fine. I mean, their magnetosphere is far weaker. Sometimes what happens is, since we have a nice magnetosphere, which acts somewhat of a shelf for us, it's actually, that's just the right pathway for us for all this to happen. For them, they don't even have it. That's all weaker, so the physics might be a lot different. So it can be either way because of the way that they're closer to the sun, and they're going to feel a far more impact, especially if it's just a CMV. The CMV is going to bring in a lot of these very clouds with dense particles in more time, which at Earth distance may not be that bad because it's going to diffuse out a lot more.
Okay,
The problem is they don't have their big magnetic fields. A lot also plays into that, so it's either way, but mostly they might have a lot more to suffer than we have.
So, Doctor, with all this mention about magnetic radiation, all those negative stuff coming out from the sun,
Yeah.
how are we confronting that? I mean, it sounds very, very, very bad. Maybe some kind of an infrastructure, like a magnetic field that can block all those.
That's something you can't do because you're really looking at a big, massive scale. I mean, all you can do is create an environment. All you can do is you can just get prepared for them. what can you do for hurricane? You really can't do anything. I mean, it's the same thing when it comes to space infrastructures. I mean, as long as you have a nice way to, warn yourselves. I think this is something that you easily contain. Astronauts always get notices. I mean, somehow, like back in the 60s, when they were going to the moon and all that, I mean, they didn't have all this exciting science to actually support them. Somehow, I should say they are lucky in many ways. If they had picked the wrong time, they knew, I mean, sun is going to act. I mean, that part of understanding is something they already had. Even in 1962, I mean, 7, 8 years before, Apollo astronauts went to moon, this is when they discovered the Van Allen radiation gravity. It's actually discovered by Van Allen. When they were launching this